detention pond sizing is a major feature within hydrology design. Many jurisdictions around the world require that engineers creating new developments design detention ponds to capture the excess water produced by the greater runoff from the impervious surfaces and run it through a pond whose storage and outlet allow the final discharge from the pond to equal pre-construction runoff amounts. So the idea that is that downstream of your developed site, the water flowing to it flows at no greater rate than it did prior to construction. It might flow longer at that rate, but at no greater absolute rate. So the process of detention pond sizing, you can think of it sort of as a two-column process. You do pre-construction analysis and post-construction analysis, all apply to a single typical rainfall event. So we've organized the commands involved in this process. You'll do the rainfall calculation once, the pre and post construction calculations involving several commands shown here twice, and then that gives you the data to do the detention pond sizing, which you do once. Then you follow up with the pond design for the detention pond itself and your outlet design. Then you have to test it to see if it works to meet the pre-construction flow conditions that you're seeking, the lower flow. And that can be done in reservoir routing by the Scs method, or it can be done very conveniently with HydroNet Explorer, which is what we're going to use in this example. So you can review the various steps over here on the right as we begin the work. Now, the command curve numbers and runoff actually works with layers and works in response to the layers set in defined watershed layers. So we will make use of these runoff curve numbers as defined here, which actually vary by soil type, except for the most impervious ones. And we will do our calculation by the Scs method. That is the method recommended most for detention pond sizing. But let's start at the top, rainfall frequency and amount. We go to the watershed pull down, select rainfall frequency and amount, and you can, if you're in the US, if you know it and you're not in the US, you can just enter it, and this works in metric, so you can enter your rainfall in centimeters. But in the United States, I can pick on my location, pick my storm event, and get a rainfall amount wherever I pick, roughly 5.8 inches, as you see here. So we have begun to complete our table. Now we're going to go to the pre-construction column and work on curve numbers and runoff. So we go to the watershed pull down, and we're going to do curve numbers and runoff. But in the pre-construction situation, we don't have buildings, driveways, or roads. So since this is so layer dependent, let's freeze those. We'll go to freeze layer, freeze our roads, freeze our driveways, and freeze our red buildings. And now we will load under the defined watershed layers our pre-construction condition. Now here we still have the post-construction developed layers shown, but because they're frozen, none of these will be used. The entire site within our target watershed, which is this blue perimeter, will use the default ground cover, which we are saying are woods in good condition. And because we've associated our soil type perimeters in the layer soil underscore groups, or whatever layer you specify here, and our labels, the A, B, C, and D, in the soil group letters, or whatever layer you choose to specify here, program will automatically do all the subdividing of the various soil types in this ground cover category and develop the table for you, as you're about to see. So we hit OK and go to curve numbers and runoff, clear what's there, select our watershed, use the perimeter method, pick the blue perimeter, and there it has found all soil groups within that blue perimeter and has given you a default, or composite I should say, calculated curve number of 46.6, which we have shown right here. Now let's continue on with the commands. Time of concentration. Time of concentration, one of the best ways to do this is the SCS method, which is an objective method. It uses the curve number you just calculated. You can pick a flow line of the original area, which is this blue line, and you can pick the average land slope by selecting a TIN or grid file that applies to that area. Hit enter for the perimeter method and pick your overall perimeter, and in that perimeter it finds that the average land slope is 5.49%, and then you can calculate your time of concentration at 0.63 hours shown here. Now, with the time of concentration calculated, you continue on down to peak flow graphical method. That method is what associates with the time of concentration by SCS, the curve number method, SCS calculation of curve number. This graphical method is also an SCS method of getting peak flow. We have our area. We have our values already inserted. Typically, you don't, in this area, we don't have any pond and swamp areas. You could put that in because that sort of buffers the flow if you had some. You'd enter the percent. And the buffering factor is this pond and swamp adjustment factor. Most parts of the country, of the U.S. that is, are type 2 storms. Just hit calculate and you can see it's calculated 9.3, 9.27 CFS. So we've completed the left side of this process. Now we can work our way down the right side, that same sort of old-fashioned method. But to do so, we go to View, Thaw, the very layers we froze. These two commands go hand in hand, freeze and thaw. So here come the layers back. Now the program's going to find these layers. But if I go to the Define Watershed Layer command, my default ground cover is no longer woods. Where I don't have houses, roads, and driveways, I have grass. So I load a different table, which would be my post-construction table. And I have open space, good condition grass set here. And I hit OK. Now I go to the watershed pull down and go to curve numbers and runoff, top item in that list. Clear what's there, select my watershed, that same blue perimeter, by the perimeter selection method, and the program calculates for all the different land cover types, cut against all the different soil groups, a composite calculated curve number of 62.1 shown here on the right. But also we note that it gives us a calculated runoff 1.94, 1.95, and a total volume of 3.7 acre feet, which is the volume of pond that would capture all the water from this rainfall event, from this 100-year, 24-hour storm hitting these various impervious surfaces of the post-construction condition. So we hit exit, and it should be clear from this process that there's a huge advantage to doing this layerizing work that we did here, because that GIS style cutting of one polyline against another is completely automatic within the command calculate curve number. We continue on to time of concentration SCS method, and we have our curve number. Length of flow is going to change because in this final design, not the blue line here, but this green line that runs over, follows the edge of the road, and finally crosses is the longest flow line. So let's pick it. Select that flow line, and it's longer than the blue one was. And our average land slope, we will say is, we don't really have a final contour map. If you did, you could compute it. We might say there's a few more edges here and there, and maybe it's gone up to 5.7%, and we can calculate, and we get a time of concentration 0.54, roughly 0.55. We're good to go. So we can use those values and continue into peak flow. Now we go to the peak flow graphical method, and we'll put in, there's the 0.54 just calculated. We have the same lack of swamps and ponds and the same type 2 rainfall event. We calculate a 32 CFS peak flow. And just to be thorough, we could go in and change our little guiding sheet here to say 32 CFS. Now we have completed the top part of this flow chart, and all we've got to do is do detention pond sizing. So we go to the structure pull down, very top item, and we use the TR55 method. That's also associated with SCS forms of calculation. So we go TR55, we have our peak inflow, our desired peak outflow, the pre-construction discharge. We have our runoff condition, 1.94. It is a type 2 storm, and we calculate a 1.4 acre-foot pond would be the minimum size pond that would handle the post-construction flow. But that pond would be the ultimate pond in that that's the smallest you can design with extremely carefully designed outlets to produce the precise original peak flow. So what we recommend is that you use that as a target, but maybe size up from there, 1.6, 1.7 acre feet, which puts less demands on you getting the outlets just right. And often a little extra pond storage is a good thing in general to give you a safety factor. So let's do what we call a bench pond design. Now in the bench pond design command, we use any closed polyline as a perimeter and then cut into the terrain with that closed polyline. So let's go to the structure pull down, select design bench pond. We're going to use a surface file for our design. You can study some of the settings there as I hit OK. I'll pick that pond perimeter, use the applicable tin file for the surface, and we'll go with the defaults. Fill slope ratio 3, cut 3. That's on the outslope. And your interior slope you can make different, but we'll make it the same. Now it finds that the highest point, or the lowest point, in that perimeter is 815. So if we use its recommended 815 top of bank elevation, then the whole pond is sort of cut into the site. And that's probably a good idea. So we'll use 815 and make the bottom of the pond 810 for a 4 feet deep pond. And it cuts it in, and then we'll get the automatic result on the stage storage, and we note that it's too small. It's only 1.2 acre feet. So we'll hit exit, and we'll say yes to redesign, balance, no, and we can size a target storage. So if we look back here, our target storage is 1.4. Let's actually size it to 1.7. We'll say yes to size, and we'll go enter target stage elevation. We'll say at 814.5, we want in acre feet 1.6 acre feet. Choose target storage units. We'll hit enter. We'll go 1.6. Here we go. Adjust the bottom elevation or offset perimeter. Adjust the bottom elevation. So now it's doing a series of iterations, adjusting that bottom elevation to give us the exact stage storage we want. Now we'll use the interval method, and we'll start at 806.5, and we'll go up every 0.5 feet and get a stage storage result. And we've got a little safety margin here. We have the necessary acre feet. Notice that we have 1.6 virtually exactly at 814.5, which was our design parameter for this. And the total acre feet at overflow is 1.75. There you see a very automatic process to get this done. Adjust parameters, no. Write stage storage file, yes. We'll write the stage storage file as pond 5. Update target surface file, no. And we will say no to these various options coming up here. Contour the pond, we won't even do that. I would point out that within this command, you can use edit bench pond and move that precisely sized pond by picking any part of it to a new position. We can just move the pond, move it slightly over if we like, and process it. We can offset it, balance at this point, and do a number of things. Balance it so we have the same amount of cut and fill. We'll just process that little move, and there's our new pond with its cut and fill condition in that new position. And then we'll hit exit. Okay. Now we have a working pond. We've designed the pond. The next step in the process is design the outlets. So we're going to make a very simple pond with a culvert running through it and a emergency weir style spillway. Now how you do that, actually we might do 3 outlets, because I might recommend putting in a baseline flow orifice. So here we go to the structure pull down and do multiple outlet design. We'll make a new file called pond 5, and we'll add first the orifice, which we'll call our base flow, and we'll just use a little 4-inch diameter orifice put in at 810.5 to remove some of the water down at that level, and calculate. Oh, and the headwater condition, I should point out, is 815. That's the top of the pond. And this little guy produces less than 1 CFS coming out of it, but it'll drain sort of the baseline flow. That's one little option. Then we'll add a culvert. We'll call this the principal spillway. We'll hit OK. We'll make it a corrugated metal pipe with diameter 18 inches. Headwater elevation is good. The inlet we'll put 2 feet below the top for 2 foot of freeboard, and actually it's only about 6 inches above the top of the pipe, spare, and the outlet, we'll give it a length of about 80 feet. If we give it a slope, it'll calculate the outlet invert, so we'll say a -2 slope over that distance. How about 2? Length 80. Oh, it's in feet per foot, so it's 0.02. and there you've calculated your outlet invert, and we can solve. And this one produces 8 CFS. So not quite enough, if you think about it, to handle our desired outflow of 9.3. So we're going to need more spillway. We hit OK, and we got one more to go. And that will be our emergency spillway, which will be a weir, and we can make it relatively small. Crest length of 4. Let's put it just a foot below the top at 814, and the head water elevation is 815. Calculate the flow, and that can punch out 13 CFS. That should be enough to get this pond to work. Hit OK. Now the key is to get a stage discharge result. Click that button, and minimum water elevation we'll say is 810.5, and it goes to 815, and we'll hit OK, and there's your stage discharge, and write the file. Call it Pond 5 to match all the other names, and we should be ready to go. Let's close this and save our COT file, which is the overall design, and let's do the final step to verify whether all of this works. One way to do that is go to the HydroCAD pull-down, HydroNet Explorer. We'll go here, we'll make a new pond design, we'll call it Pond 5. Now we'll load a pre-stored rainfall event, which is that same Maysville, Kentucky rainfall event, 5.8 inches that we started with. I had that pre-stored. We'll also go to the setting button and note that we have the rainfall event already there, but we do need to get under the general pull down, a general tab, a surface file. So get our surface file picked, and you could have defined your rainfall event directly within the settings button, or loaded it and then added your surface event. Now, this up arrow is a very automatic update button that will read these various layers for the final condition in response to the watershed layer definitions and populate our subcatchment dialog here, our options. So we hit OK on that. We're not doing the lower item. We're not outputting to HydroCAD in this instance. And it created one new subcatchment. You will get a little problem here if you use any of these layers elsewhere as text on the drawing. Then it'll try to use that text and apply it to soil types and other things. So be sure that the layers associated with this hydrology design are used only for their design purpose. Now, if I right-click the 1S that's come up, it found that watershed by name. If I right-click it and hit Edit, I can see its hydrograph. And you can see that it is that same roughly 32 CFS calculated in the post-construction condition within HydroNet Explorer. So they match. It's another way of doing it. Now, what we want to do is add a pond. So we right-click the pond and add a pond here. We'll call the pond number the default. We can give it a name, Pond 5 if we like. And we can select the available inflow and add it to what goes into this pond. Now we need to load our stage storage, so we go Edit and load a stage storage file, which we have as pond capacity, which we've just saved, and hit OK. And we need to edit and load or add a stage storage. Hang on, we just want to add a stage storage event here. So we load Pond 5, and here comes our stage storage information, our stage discharge information, excuse me, for our multiple outlet design. We've used the load button twice here. Tailwater elevation means you're not coming in submerged, so 0 applies to our situation. Hit OK. So by clicking the Edit button and then following up with the Load option in both cases, we've loaded our prior designs of pond size and stage discharge. Now we have everything we need, and more tabs have appeared, so we can actually see the stage discharge and we can see the stage storage curve for this particular example. And if we go to the Hydrograph, we get two curves. We get our 32 peak, and we get our peak discharge as reduced. In this case, we've reduced it to 9.8. Our target was 9.3, and that's extremely close to our design goals. Now what we'd want to do is perhaps restrict our culvert pipe to perhaps 15 inches and or do other design edits if you wanted to continue on in the process to get down to the 9.3 target. But that is the procedure for going all the way from a layer-based design drawing utilizing the layers defined in the Watershed layer command, following up with detention pond sizing, bench pond, multiple outlet design, and concluding in the HydroNet Explorer as a method of designing your detention ponds to meet pre-construction flow conditions.